So the first group had the question, if we look at the subgroup I and R to the fourth power inside of D8, that's a normal subgroup. And I was interested in hearing your group talk about the factor group, D8 mod H, for this subgroup H. So Hart's group, tell me about your process. So what did you say, first of all? How many elements will the factor group D8 mod H have?
It's 8.
8. And how do you know it's 8 elements?
Because the order of the factor group is going to be the order of the big group divided by the order of the subgroup.
Yes.
16 divided by 2.
Great.
8, yeah.
What theorem is that, by the way? Well, it's a textbook theorem, but it's associated with a particular person. Anyone? Lagrange. It's Lagrange's theorem. The number of cosets that H has in D8 is the same as the ratio of the orders of D8 and H. All right, so we know for sure that this factor group is a group of order 8. The question is, which group of order 8 is it? I didn't ask quite that broad of a question, but I did ask you to at least tell me whether or not that group, whatever it is abelian. So let's see. Can I actually get all my elements here? 1, 2, 3, 4, 5, 6, 7, 8. And my original subgroup was I and R to the fourth. All right. So did you guys decide, did your team over here decide whether or not this factor group can be abelian?
Actually, it's no.
So you said it was not abelian, and how did you demonstrate that?
Well, we picked two different, I don't know how to say it. Is it
Cosets.
Elements?
Yep,
Cosets?
elements of the factor group or cosets of the big group.
Cool. So we picked two different cosets. We picked TH and RH.
Okay, so I'm going to write those on here. RH is going to be R and R to the fifth. TH is T and TR to the fourth. Okay.
And then we wanted to check if TRH equals RTH.
Right. And so TRH is going to give you, what is that? TR to the fifth?
Mm-hmm.
Yeah.
And what is RTH going to be?
RTH is going to be RT and RTR to the fourth.
RT and RTR to the fourth. And when you simplify those, RT is going to be TR to the seventh,
Yep.
right? TR to the seventh. And RT times R to the fifth is going to be, it's going to be R to something. But the point is, this TR to the seventh belongs to one of these cosets and not the other. So these two are not the same. Right. So this factor group is not abelian. Why was this a more interesting question for your group than it was for the diamonds group? So the diamonds group started with this subgroup of 4 elements in it. How big was its factor group? Factor group's got 4 elements in it in this example. And so why is it a much less interesting question about whether that factor group is abelian now?
Because all groups of order 4 are abelian, it must also be.
Yes. All groups of order 4 are abelian. There's no way to make a non-abelian group of order 4. Don't answer this because I want to ask the rest of the room, and you already have. What's the smallest non-abelian group? How many elements does the smallest non-abelian group have? It is? It is? Say again? No. The smallest non-abelian group has what order? Smallest non-abelian group. The smallest non-abelian group is the dihedral group of the triangle, 6 elements. By the way, what about the symmetric group on 3 symbols?
Unfortunately, it's abelian.
Symmetric group on 3 symbols? It's not abelian. How many elements does it have? 3 factorial, which is 6. In fact, D3 and S3 are isomorphic. They're the same group. Okay. Coolness. Let's talk about problem 2. The group in the middle was working on the problem that says A5, the alternating group on 5 symbols, is a simple group. And so you're supposed to then deduce that any homomorphism from A5 into the cyclic group of order 60 must be trivial. So you all had a nice diagram that I kind of want to copy before we start talking. So you have this hunters and arrows kind of diagram for a homomorphism from A5 to Z60. Right? Z60 is the additive group of integers mod 60. So 0, 1, 2, up to 59. Clearly not going to write all the elements, right? Meanwhile, A5 is a bunch of permutations. They're all even permutations. So I've got things like 1, 2, 3 in here, 1, 3, 2, 1, 2, 3, 4, all kinds of stuff, tons and tons. But remember the hint that I gave you? The hint is that what's the order of A5? What's the order of Z60? 60. So these are two groups that have the same order. All right, and we've got some homomorphism between these two groups. So, group in the middle. How did you make the argument that this must be a trivial homomorphism? Where does this argument start?
A5 is not commutative and Z60 is commutative.
Okay.
So A5 cannot be, or is not abelian and Z60 is abelian.
Okay.
So they can't be isomorphic.
All right, so that's a really key assumption or key observation for later on. Thus, A5 is not isomorphic to Z60. So we're going to keep that over here in the parking lot because we're going to need that fact to make this argument. Okay, but what does that have to do with the existence of a homomorphism between these two groups? Because we can have a homomorphism from a non-abelian group to an abelian group. That's okay. We can't have an isomorphism. We can have a homomorphism. So what are the other pieces necessary to make this argument? So tell me about, let's start with the kernel of this homomorphism. Where does the kernel of this homomorphism live in this diagram? It lives back here, right? So the kernel is some set of elements back here. The kernel of a homomorphism out of a group has to be a normal subgroup of that domain. So, given that the kernel of phi is a normal subgroup of A5, what does that mean about the kernel of phi in this problem? It's either all of A5 or it's trivial. Right, so that's why I had to give you this information at the beginning of the problem that A5 is simple. Right? Because it means that there's only two possibilities for what the kernel of A5 can be. It can be the trivial subgroup, or it could be all of A5. So how do we know which one it is? So let me ask the what if question. What if the kernel were all of A5? What would that mean about the homomorphism phi? We're jumping the gun a little bit here. If the kernel is all of A5, what does that mean? What is phi doing if its kernel is the entire group A5? It's sending everything to 0. Exactly. So then, phi of x is equal to 0 for all values of x in A5. And by the way, that's supposed to be the conclusion that we're drawing here, right? So we want to show that this must be the case. Which means, by the disjunctive syllogism, we need to outlaw the other possibility. So what would happen if the kernel of phi were trivial?
Then there would be an isomorphism between A5 and C60.
Why? Tell me about that.
Because a homomorphism between two groups with the same order has to be an isomorphism.
A homomorphism between two groups of the same order must be an isomorphism. Why am I pausing on that statement?
Because homomorphism is like more simple than an isomorphism.
Yeah, because we could send, it's a homomorphism to send all these elements to 0, right? That's not an isomorphism though.
A one-to-one.
There we go. That's the key. Phi would be 1-to-1 in the case where its kernel is trivial, right? Just like in linear algebra, when the null space of the linear transformation consists only of the 0 vector, that's a 1-to-1 linear transformation. Phi would be 1-to-1 if its kernel were trivial. But then I would have a 1-to-1 homomorphism between two groups of the same order. So what else would it also be? would be an isomorphism. Yeah. But why is this impossible? Because it's not because A5 is not isomorphic to Z mod 60. Right? So therefore, we can rule out this possibility. This can't happen, and therefore, by a disjunctive syllogism, the other thing must happen. Right? The kernel must be all of A5, and therefore phi must be trivial.